Okay, I'm briefly going to walk you through the schematic of my version 3 analog safety converter. We're starting with 24 volts AC. This is a very common voltage. If you're in industrial automation, then you would probably expect to see like a 24 volt DC starting point for something like this. But in the HVAC building automation world, 24 volts AC is kind of a more common starting point. So that's where I've decided to start this with my voltage regulator. I'm stepping down to 5 volts DC. This is an LM2576. And so basically we're rectifying this using a diode and capacitor, which is going to give us a steady roughly 33 volts DC coming into our voltage input of our LM2576. Of course, the ground pin is going to go to ground here. Our output goes to a 100 microhenry inductor. And so then on our output here, we've got 5 volts DC, and of course we got that going back to a feedback in that voltage regulator there. So we're feeding 5 volts DC, and I'm just going to use a single input as an example. So let's just use input and output number 3. So this 1 mega ohm resistor will have a tendency to pull this side up to 5 volts DC unless it's being pulled directly down to 0 or to ground. And what I have on our voltage comparator here, this is an LM339. On our input number 3 input negative here, we've got 2.5 volts because I'm taking this 5 volts DC and using a voltage divider, this side here being ground, using this voltage divider to drop that in half to about 2.5 volts. So if this is above 2.5 volts, then this will be higher than this, and our output will be high. If this is pulled to ground, then this 3N positive will be lower than the negative, and our output 3 will be low. And this is going to be, in our safety circuit, this is going to be the default. This is what we want. We want our output 3 to be low, and the reason is because it's going to go to another voltage divider here. If you follow this line from output 3 of our voltage comparator, it's going to go to another voltage divider here at VL3D. It's going to go across a 4007 diode to our analog output. Okay, so when this is pulled low, then our 5 volts is being fed from here. 5 volts is going to the top of all of these resistors here to the voltage divider. So the voltage divider here, if this segment here is at equal potential with ground, then this is going to pull this to 0. We're not going to get any, or we're going to get negligible voltage to this side of the diode. It's just going to drop to 0. So we're going to get 0 coming out. Now, if the output goes high, it's going to do something different. And what will cause the output to go high will be if this is pulled up above this. So remember, this was 2.5 volts, and our 1 mega ohm resistor here is a pull-up resistor. So if our ground is broken from either our safety circuit going out 5, coming out or coming back in 6, if that safety circuit opens, or if we manually flip the test switch to open, it's no longer being connected to ground right here, then this will cause this to be pulled up to 5 volts. This 1 mega ohm resistor here, it will be pulled up to 5 volts. So then our positive will be higher than our negative here in the comparator, and output 3 will go high, which essentially means it's just going to float. And by float, I mean it's going to act like it's like you just disconnected it. And then our 5 volts coming in here will be going through this voltage divider, and because of our ratio 330 ohms, and on our bottom resistor here, 1500 ohms, that will give us distinct voltage back to our analog output to be read. That will be somewhere between 0 and 5 volts for each of these voltage dividers here. Now, what makes this version 3 different from the version 2 is this addition of this condensate sensor. And so we've reduced the safety circuits to 3 normally closed contact safeties, and then of course the condensate safety. Now this is the sensor type. Now you can always use version 2 if you have like a condensate float switch that has a switch built in, but you may be putting this in a device. Now see, this is version 2, that's why we have safety 4. We have safety 4 out, safety 4 in. But in version 3, we just have 3 of those switches. But with the condensate sensor, what it's trying to do is it's trying to find a path to ground. And so you would want one of your probes to be at ground or equal potential if you don't have a metallic condensate pan, like a stainless condensate pan. If you do, then you could just take this ground to the chassis anywhere. And this will usually work just having a single probe dangled over the condensate drain. But if you have a plastic pan in this application, what you want to do is take this to the chassis and also take this to one of the probes. So one of the probes would be equal potential with ground, and this condensate sensor is trying to find a path back to that. Now, when you're calculating your resistors, you want to keep in mind that the conductivity of condensate is much lower than just tap water. So if you're doing some bench experiments, don't expect to get the same type of conductivity in your condensate. So let me show you on the schematic how this condensate sensor works and how it's used just in place of that 4th safety. Back at the LM339, we're going to be using input-output number 4. And what we're doing differently with this condensate on this model is I'm taking my 2.5 volts that's coming after my voltage divider here, and instead of feeding into the negative like I did on the other inputs, I'm feeding this one into the positive. Okay. Now remember, output 4 is going to remain in a low state, which would be a no-fault state. That'll be syncing this to 0 volts, so we're not getting anything coming through this diode here. So that'll be a no-fault state when output 4 is low. And to get that low state in output 4, we need this positive here to be lower than our negative input here. And so this is going to be pulled up in a no-fault state by our 1 mega ohm resistor here. It's going to pull this up to 5 volts, keeping this higher than this, keeping our output 4 low. Now what's going to happen either in a test state when we switch this safety here to ground, then it's going to be pulled low. Or if this can find a path back to ground through the conductivity of the condensate, either to the ground probe that you've put in or to the stainless condensate pan that's grounded, if it can find a path back that's able to overcome this 1 mega ohm resistor, which isn't difficult, if it can find that path back through the condensate, that's going to pull this below the 2.5 volts. It's going to pull it, 0 or practically 0, close enough to 0 that it's going to be below this 2.5 volts we have coming in here. That's going to make output 4 go high. When output 4 goes high, remember, it just kind of floats, or it behaves as if you just disconnected this. So our 5 volts is going to be able to feed through here, feed through our 330 ohm resistor, through our diode, and give us almost 5 volts. It's usually like 4.7 volts on our analog output going out. So now we still can read 4 distinct voltages coming out of our analog safety converter, but we're only using 3 dry contact safeties and 1 condensate sensor. Again, you could always use version 2 if your condensate sensor is just a condensate switch. But not all HVAC equipment has that already built in, and sometimes it's more convenient to use the sensor that's already there.